So we would like to give the statement of the Uniform Boundedness Principle. So according to this, we have a family of operators of linear maps between two Banach spaces, and we have a condition that holds pointwise, meaning for every point of the domain of definition. And that translates to a condition that holds pretty much uniformly. Well, let's see what this means. So let X and Y be Banach spaces. And T sub I from X to Y, a bounded linear map for I and I. So in other words, we have a family of bounded linear maps. So we have a set I, which is an index set, and that index set allows us to index a family of such bounded linear maps. If the set Ti of X for I and I is bounded, so what we mean by bounded is this is a subset of Y, right? Because it consists of outputs of these linear maps, is bounded in Y for every X in X. Then the much larger set T sub I of X for all X whose norm is less than or equal to 1, and all the I's and I's is bounded in Y. Equivalently, there exists M greater than 0 such that the norms of all these Ti's are less than or equal to M for every I in I. The usual application of such a theorem is to have a to have a linear map which is defined by a limiting process through bounded linear maps, and use this result in order to show that it's continuous. So in fact, we could have this as a direct consequence, and this direct consequence is usually known as the Banach-Steinhaus theorem. It's a very interesting story to read about Banach and Steinhaus, how these two mathematicians were related. It's a really fascinating story, but it's not of the moment. So all I would like to do here is just give an indication for the proof of this theorem, which is not hard at all, and it's seen to be a very nice consequence of the bare category theorem. So this is a direct consequence of the bare category theorem. I would like to give the outline of the proof. And the outline is as follows. So consider Kn to be all x's in X such that Ti of X is less than or equal to n for every I9. So what are we doing here? We're pretty much taking the upper bounds. You could take the least upper bounds of the numbers T sub I of X. Remember that according to our assumptions, this is a bounded set, right? So this is going to be a bounded set. Oops, by accident I erased something. Let's put it with the right. So this is a bounded set. And the bounds for these numbers are going to be different depending on the x. But if we define one such set for every natural number, then eventually every x will be in such a set. So in other words, we can argue here that the union of all these kn's is equal to the space X. And now, because of the continuity of the linear maps, it follows that all of these kn's are closed. In X. That's because of the continuity of these maps. It's easy to show that if you have a sequence that belongs in the Kn, then the elements of the sequence give you norms for each of the Ti's less than or equal to n, and so the limit by continuity will give you the same thing. So the Kn's are closed. So what we have is that X is the union of a countable family of closed sets. Now remember that these sets cannot be meager, right? So they cannot be nowhere dense, meaning one of them needs to contain an open ball. One of these sets needs to contain an open ball, or a closed ball of positive radius for that matter. An open ball or a closed ball of positive radius. So what does this mean? It means that all the operators are bounded. Think of the Banach space X like this, and all the operators are bounded on a closed ball of positive radius. So they're bounded by number, right? So what you could do is really transfer this ball to the origin and dilate it so that it becomes the unit ball. And through very, very elementary arguments, you can see that all of these operators are bounded on the unit ball, which means exactly this. That this set is bounded, which means exactly that all the norms are bounded. So it's a good idea for one to actually look at this translation of the small ball, which is centered at some other point to the origin and then its dilation. But pretty much that's the basic ingredient of this proof, which is a very simple step. If you have not done it before, it needs a little bit of work, but it's still a very simple set, and that shows you how the uniform boundedness principle is a direct consequence of the Baire category theorem. And that's all. Thanks for watching.